morning, welcome back to the course. I am Dr. Amandeep Singh and I will take the plant simulation Technomatix in this lecture. I like to talk about the distributions. Okay, I have just opened this milling process. The processing time is 1 minute. If I put uniform distribution you know that is also known as rectangular distribution. So, where we have just the start and stop, we have the minimum and the maximum value, and we know that the value would lie between these two values. We do not have much information. So, uniform distribution and triangular distribution and beta distribution, these are sometimes known as the lack of information or lack of knowledge distributions, because we do not have much past knowledge. We just have 2 or 3 or 5 or a very few number of observations, and we do not know what a distribution would it follow. We have just a minimum value and maximum value. We do not know what is happening in between. So, we just pick this rectangular distribution. If you remember, if you know, the rectangular distribution is just we have A value and B value, that is all. So, it is showing, if we have to put it in this way, stream, start and stop. So, I will just put start and stop. Let me say the minimum time is 2 minutes, okay, and the maximum time is 3 minutes. Okay. So, this is there. Now, I have just put start and stop, I have not put any stream. What is stream? If you know about random numbers, stream is the seed of the random numbers. So, when we talk about the simulation, what is simulation? Simulation, we are trying to imitate the reality, and what is representing the reality, what is representing our actual real objects or subjects, it is the random numbers which you are working on. So, where does our random number start from, or the specific? So, that is a stream. So, if for instance for there are two processes, I put the same stream here. Same stream means the random number will start from the same seed and the successive random numbers would be same. For instance, if I put the seed value 2 here in one process and seed value 2 here in another process, so the 9th random number that is selected in this process and the 9th random number that is selected in this process, that would be same, 9th, 5th, because the seed is same. So, the successive random numbers would be same. So, it is recommended to pick a random seed, not I would say random seed, but at least a different seed for different processes to have the good simulation process. So, if we do not put any stream value here, the software would pick a stream value by itself. Okay. So, I am not putting any stream value. So, I have just put uniform distribution. So, we know that the minimum time would be 2. Okay. Or let me say the time varies from 2 minutes 50 seconds to 3 minutes. We know that this is the minimum, this is maximum. Okay. First I will talk about triangle distribution. Triangle distribution is actually sum of 2 uniform distributions. 2 uniform distributions are there. 2 uniform distributions means just have the smallest value and the largest value. We do not know what would happen. But in triangle distribution, we have 3 values. We have the smallest value, we have the largest value, but we have the one value that is in between, but repeating for the maximum number of times. It is repeating for maximum number of times, that is the value is mode. What is mode? Okay, like mean, median, mode is there. Mean is the central value, mean is actually the average of the values, median is the central location value, mode is the value that is having maximum frequency. Okay. So, here we can put, if I pick the triangle distribution, it is showing stream C, A, B. Here A is the smallest value, B is the largest value, C is the mode value that is repeating for maximum number of times. When it is repeating, I am talking about the past data. In the past data, I have 5 or 6 observations. I know this is the minimum value, this is the maximum value, but there is one value which is trying to repeat maximum number of times. So, I can pick the triangle distribution. Based upon the past data, if I have a lot of observations in the past, I can pick normal distribution. Okay, if that fits good here. In normal distribution, it is asking for its parameters. Okay. The normal distribution, I would say normal distribution statistic it is asking for stream. Now, it is asking for mu and sigma. Mu is the mean or average, sigma is the standard deviation. Also, it is calling for the lower bound and upper bound. Lower bound is the minimum value and the upper bound is the maximum value within which our distribution would lie. So we should have the knowledge of the distribution. As I said, the softwares are GIGO, garbage in, garbage out. So if you put the right distribution and you have the right numbers, and be having the results of the simulation very close to the realistic conditions. So this is the work of a systems engineer to design it in a proper way. So if I change this time, you can see, okay, I do not apply, okay, because it is okay, it is showing, you know, if I do not put it in a proper way, this is stream mu sigma. I am showing the value of stream, it has just picked. I was showing the value, that's 250 and 3. The value of mean was smaller than sigma. So that is why it said, okay, it is showing the negative value, it is not accepting, it wouldn't accept any other format than is required. So let me pick just constant time here, and it was, just to make you understand properly, it was 1 minute I will apply. So let me see if I run it for an 8-hour day and try to see the throughput, open, you try to see throughput, the throughut per day is 1167, okay, per hour is 48, okay, and the total throughput is 389 for an 8-hour day, for 8 hours. Okay. Now if I change the processing times, open, if I change this processing time to, let me take 2 minutes, okay, and I change this processing time also to 2 minutes, in actual conditions we cannot change the processing time. The processing that it has to take, it would take. The milling, it has to, if it has to take 2 minutes, unless we change the tools, we change the machine, or we have the CNC machines, or we have the advanced machines, we cannot but work on more on the processing times. The processing times are fixed. Yes, in the plant simulation or in the manufacturing simulation here, we can think of working on the bottlenecks. The processing times are fixed. We can think of designing the layout in a way that the material flow is minimum and that the total time taken is minimum. Total time taken would be minimum, that means the total throughput would be the larger. Okay. So if I change this time, now I have increased the time to 2 minutes. Now I run the process and let me try to see the throughput here. You can see the throughput was larger before, so it has reduced now because the processing time is increased. Okay, it is 582 pieces per day, 194 pieces in a 8-hour day. Okay. So also we can have the setup time as well. For instance, a workpiece is to be manufactured, it will take 2 minutes for processing and 1 minute for setup. 1 minute for setup means, for instance, some milling is happening. If you have a milling process, what do? We just rotate the tool and remove the material. So it is removing the material from one workpiece. This is 2 minutes process. After 2 minutes, the machine stops, this workpiece is taken off and a new workpiece is brought in here, that is the raw one, and it will start process on this. Now this setup takes 1 minute here. So this is setup time. This is setup time, this is processing time. If I induce setup time as well and apply, let us see what happens to my throughput now. Only in one line I have put some setup time. So the throughput is further reduced here. It was 197 pieces, so it is 194 pieces now. Okay, because the setup time is there now, another 1 minute is being taken. So total time taken in the milling process in the line 1 is 3 minutes now. Okay. So this was a brief introduction about the software, the major or the main objects that we can use. Now I will pick some examples. I have some examples for you to show you different layouts, and also the experiment manager will use. We will try to see the simulation that we can do in the software. So this is continuous material flow. I will select 2-lane track here. So traffic circle or segment table. Traffic circle, pick and open the model. Okay. So this is the model, it is already running. So I will just run the model. You can see, okay, this is the trolley that can pick our material from. So this is source part, some processing is being done here. I can see what is the time of the processing here. The time is constant 1 minute. So you can see it is happening. Okay, I will make it a little faster. control panel, I will make it a little faster and then run. Okay, this trolley is running, trolley is continuously running through the tracks. Okay, this is actually about 20 times faster. So the processing is happening. Okay, it has happened for the 9 minutes. It is not stopping. So what is the setting? So there is no end time, so it will continue for the infinite time. So this is a kind of just a cell, an O cell. Okay, so cancel, stop. So segment table, open model. This is just showing a track. Okay, how the track is built. So let me pick user interface. Okay, dynamic statistics, display panel or chart, open. So in this model we can see the chart. What is setting? There is no end time. I will put the end time here 080000. Apply. Okay. Let me try to run this model. So it has run for 1 day. So entity buffer is there, entity machine is there. This is similar to that. So we can see the charts here. Show chart. So for only one machine, it is showing the chart that okay, this is something unplanned. Blue color is unplanned. Then we have blocked. Then we do not have any failure here. We have this waiting time for the about 37% of time it has been working. So this is another example. Okay. Then tools and optimization. Okay, the important is experiment manager. I'll just pick the buffer line optimization. Okay, this is line comparison open model. So in this model, what we have 3 lines. Okay, in this line there is throughput with no failure, there is throughput with failure and buffers. So there are buffers kept in between. If I enlarge it, this is buffer. Okay, this is another buffer. So you have kept buffers in between. This is throughput. We need to see throughput with no failure. Another line is throughput. We have put some failure rates here. Okay, if I see the failures, it has 90% failure, 90% availability, it is 10% failure. In this case, there is no. In the first case, there is no failure. Okay, so let me try to run this model. Yes, this model has run for an 8-hour day. So for with no failure, the pieces those were produced in a day were 477. With failure it is 347. But because failure is there, we have put the buffers in between that can store some of the material. So it is about 417. So also it is giving the percentage of the maximum throughput. Maximal throughput is 477. So it is with failure we have 72%, and with failure and but with buffers we have 87% of the throughput of the maximal value. Okay, then I can then in resources I can see broker and animation. So shift calendar, worker. Okay, I will show you a worker introduction. Okay, worker introduction model. So this is the worker introduction model. So in this case you can see the workers are just introduced into machine, and if we run this, okay, let me try to make it a little slower. Apply, now run. You can see the workers who are running it. So I can see the number of workers are 2 here, and work pool is there, and the broker is there. Broker is trying to distribute the work to different workers. Okay. So this is one of the example. Then okay, let me come to the major simulation thing. That is the experiment manager. tools and optimization, experiment manager. Okay, this is one of the models where we have experiment manager. This experiment manager can show the simulation. Okay, if I run this model, or let me open this experiment manager first. It's at definition and evaluation. In definition, we have defined the output values. Output value of the workstation portion, start fail portion, it is working and failed. So what output do we need, and what inputs do we have? Input is the route delivery and mean time to repair. Okay, so if I run this model, so also I can define the experiments, that is for number of 100 number of parts, mean time to repair is this much, 5, 10, 15, then 5, 10, 15. This is for 100 parts, this is for 200 parts again. So these number of experiments would run if I run this experiment manager. Let me try to run. It has run for 8 hours. Okay. Now let me try to see experiment manager. Now I need to see the results. It has shown the results at the mean time to failure. If it is kept 5, so it is working for this much number of time, it is failed for this much number of time. So for the simulation of 100 parts, for the simulation of 100 parts again, okay, this is for 200 parts. So it has taken 8 experiments. So I can see the report as well here. Okay, in the report it is telling that, okay, there are number of experiments. In experiment 1 this happened, in experiment 2 this happened. Okay, this is the total failure, this is blocked time, then gray color is waiting time. Okay, all these things it is telling in the report. So in experiments, what has it taken? It has taken different random numbers. In experiment number 1, different random numbers are taken. Experiment number 2, different numbers are taken. What is experiment number 1? It was given here, the inputs that we gave, output values are here in this results. Experiment number 1 is 100 parts with mean time to failure as mean time to repair as 5 minutes. Experiment number 2 is 100 parts with mean time to repair as 10 minutes. Okay, so it is showing these experiments here. So we can have all different kinds of designs. Then rule, we haven't defined any rule based setting can also be done. This is, and like if we go to the detail of the simulation, these things are possible. So now, okay, layout optimization, factory optimization. Factory layout is there. This is a factory, and we have made weird kind of connections here. So layout optimization can be done for where to keep what machine, then what would be the overall, what would the maximum throughput if we do that. So these models can be also, we can go through these things to find the optimization here. So another model I can pick here is from continuous material flow, tool and track, distance control. Okay, sensors are like if we need to, for instance, if we need to accelerate at some point, or we need to put brakes, or we need to put the, okay, this is a light, and like we can do anything. Let me open this model. Okay, yes, this is an brake and accelerate model. So I have defined the method here, watch method. The method here is brake and accelerate. So if I try to run this model, okay, first let me see the event simulator. It is end time, okay, nothing. But just to see whether how it runs, you can see this is brake. After brake, it will just slow down. After accelerate, it will accelerate. This is speeding the speed. So at this point, brake would apply. It is accelerate now. The brake would apply. It will take a turn, accelerate. It will accelerate from this point. Okay. So this is a kind of an entity. This car here. Okay, we had just one kind of entity. This is another entity which is in the form of car. Okay, the name is auto sorter. So this was by sensor in continuous material flow. There are many models in this. Okay, so I'll just pick randomly something, okay, tools and optimization. I can pick experiment manager. Then I'll try to explain the experiment manager in more detail. I'll pick an example. So before that, let me pick something Okay, transfer station. Okay, transfer station, I have a demonstration model here. Transfer station is, this is one cell. Okay, this is one cell, this O is one cell, this is another track here, two-way track. Okay, transfer station, it will just transfer the material from this cell to this track. Let me try to see the event simulator here. You can see the trolley or the container came here. Okay, the container is coming, some machining is happening here, some machining is happening at this parallel process. Okay, let us first see what are the process parameters here. This is a parallel process in which 2 into 2 4 processes are there. The times is again the default time 1 minute. Okay, so if from source it comes and transfer station is there. We need not to connect transfer station. Transfer station, when we see the transfer station, so it will transfer, it will load, it will just load the process. It is connected, connect paths from the parallel process. We just need to put the name of the process, from which process it will pick the part from parallel process. Okay, then it will target or transfer the parts to line. Okay, so there is no connector required in between. We need to just mention the predecessor and the successor processes here. So sensor position is this one. So all these, so we can select load, unload, reload, move. So it is loading the parts. So all these attributes availability is 100%. We can select this. Okay, I wouldn't change anything, and let me try to run the simulation. So these containers are running, some processing is happening here, it will taking 1 minute. So transfer station is then transferring the part to this container. So this container is just coming here, and this transfer station, it is connecting the part from this line 1 to the two-way track. Okay, if I see its properties, it is from line to the track. The name of this track is track only. Okay. So again from this there is another transfer station. Okay, there is source transporter as well. The source transporter, that is a source is there that is trying to transport material from some other frame or some other, using some other interface. It is trying to do that. So this is one of the objects that can be used. Okay. So this is just a transfer station. Okay. Now apply. Okay. So there are certain examples which are available for us to see how these things happen. As now you know what is factory simulation, what is Technomatix, what is plant simulation 10, some of the objects we have discussed in that, and some of the libraries we have discussed. Now let us talk about rapid manufacturing. As I discussed, the factory for rapid manufacturing could be like this. This is a factory for rapid manufacturing. In this we have different sections. This is specifically additive manufacturing section. This is CNC. This is heat treatment, right? Before additive manufacturing, it can be some maybe design here or CAD. That can be in the factory, or maybe it is controlled out of factory. So this all setups are there. This is a kind of a process layout again. Now one of the factories is, this is additive manufacturing. You can see this spool here, that is 3D printers are working and only one worker is trying to set the machines. Then the machines as are automated work by themselves, so workers is just spending some time on this setup. So this is the factory that is given by Siemens. So also, as I said, these are the workers, those are working on different machines here, and some of the machines, the CAD model is controlled directly from outside. This is again, as I said, cloud based manufacturing. Maybe Wi-Fi is working. Okay, so I have a factory for you. This is a hypothetical factory in which you have different processes here. These are single processes. If I put the names on, this is single process 1, single process 2, single process 3, right? And then we have inspection and packaging. Also we have a second line in which we have a single process and inspection and testing. So what are these processes those I have put? This is selective laser sintering. So first what happens, let us thing that is sintering of the metal products or metal additive manufacturing. So this is selective laser sintering here, and the second process here is CNC process, that is post processing, that is taking place here. After that, this is heat treatment. After that, inspection and packaging. So we are talking after the CAD model is received, the STL file is received from the CAD model, and SLS or selective laser sintering has happened. So this is one line. Okay, this is something I have put a flow line that has a kind of a big batch to work on. So the machines are automated. There are workers who are working. This is work pool where the workers are being controlled. This is the second line in which this is fused deposition modeling or 3D printing, and this second line is put as something customized products or specifically order based products or job shop production, I can say. In job shop production, only one job come. We don't know what will be the size and what will be the time that will be taken, so variability would be high for the second process. So let us try to demonstrate how does experiment manager works here. In experiment manager, we'll conduct 25 experiments, each having 50 observations. So what are input variables here? Input variables are this selective laser sintering processing time, selective laser sintering setup time, then CNC processing time, CNC setup time, then the third process, that is heat treatment processing time and setup time, then packaging is just the processing time, and then is the second line of 8, 9, 10 points are for the second line, which is fused deposition modeling or 3D printing. This is the processing time, setup time and packaging time. So these are inputs. What are these times? Let us see. Those are put here. So these times the distribution is kept constant here. It is constant distribution. It takes this time, this much time here. Okay, and setup time is this much. These times are generally observed before putting into simulation. A few pilot experiments are conducted, and those times are put in here. And those times are then used to conduct simulation for having the feel of the realistic environment when we'll have a long run. So these are the times for the single process one, that is selective laser sintering. So let me see, this is FDM. So time is around 70 minutes, and this is setup time is this is constant. The distributions are taken constant. The distributions can be selected in a way depending upon the process that we have chosen, as I have said. In case of the selective laser sintering, because I have taken first line as a big badge, so we might be knowing that what is the time, so that can be taken normal distribution. So those distributions are put here now. After putting those distribution, these are the input variables that I just showed. These are the experiments. Different experiments, 25 experiments would be conducted, total 25 experiments. Times for selective laser sintering, setup and processing time for this, setup and processing time for CNC, all these times are put here. So 25 experiments, and for each experiment we have put observation per experiment. That means each experiment would be repeated 50 times, and that would give a result for one experiment. I can consider one day. So I have put this time as an 8-hour day here. Okay, so one experiment would run for 50 times for 8 hours. That means total experiments that would be conducted would be 25 into 50, that is 1250 experiments. So 25 experiments for a single day would be conducted. So let us try to run this simulation and see what are the results those are coming. You can see this is current experiment. This 6th experiment, 7th experiment, observation for 8th experiment. These are observation, 50 observation would be conducted, would be taken in. It will also show how much time has it taken for conducting this simulation. This is a very small and hypothesized simulation. When we conduct actual simulation, the whole factory, the number of parameters, those are set. So this is finished. The total running time was 38 seconds for this simulation. So they have shown the results here. I have put it in a default that we need to produce a report here. So this is the report that they have produced. The model is this one. So these are the units, those are moving. Okay. So this is the overview of the timing that we have put here. These are the values for the experiments. So the output values of interest, you can see this is the output for line 2, throughput line 2 output. So let us first show you the output for line 1. So in this window you can see we can publish the results. What variable do we need to produce? Let us say throughput line 1 first, throughput line 1, okay, and report is show. Throughput line 1 is like this. You can see, as I said, in throughput line 1 we didn't put variability very high. The average value here is around 170 and the standard deviation is around 4.5 or 5. So which is around 2 to 2.5% of the mean value. So this is stable variability in case of line 1. We have different machines. You can see in the case of experiment number 5, this is the box plots, those are produced. So in this box plot you can see the lower whisker is coming this low. The box plot is something in which we have this point as median, this is median, this is quartile 1 and this is quartile 2 and this is quartile 3 here. So this is trying to replicate the realistic situation. So in realistic situations sometimes it might take, might produce very less number of units in a day, in day 5 maybe, experiment number 5. In this one box plot means 50 observations. Total 25 days or 25 experiments are conducted. One box plot is 50 of the observations. Out of the 50 observations, this is the median, this is the maximum value and this is the minimum value. Okay. This is line 1. Now let us try to produce the report for the line 2. So detailed results can also be produced. Now let us pick the variable line 2 and tell them to show. Now this is line 2, you can see the variability is quite high. The reason for this is that number 1 is the number of units those are produced is only 14 is the average here. It is only 14, maybe from 10 to 19 pieces are produced. From 10 to 19 pieces are produced and average is around 14. Okay. Out of these 14 units, the standard deviation is 1.5, around 1.5. So 1.5 out of 14 units is around 10 or 11%. So this is a little higher variability than we observed in line 1. So this is something that we have job shop production, as I said. The products are coming, we don't know what is the specific product that we are going to produce, what time it would take. So that is why the variability is quite high. So this is simulating the job shop and the batch productions here. The starting point for this simulation is selection of number of workers. You can see there are 4 workers, those were selected finally. The starting point was actually 6 workers. 6 workers means one process has 1 worker, corresponding 1 worker. There are total 6 processes, you can see 1, 2, 3, 4, 5, 6. It was assumed that each worker has equivalent skill set. They can work on any machine, post-processing, pre-processing, selective laser sintering, fuse deposition modeling. This is not the actual case. Generally, when we talk about additive manufacturing, the workers might have different skill sets, but to simplify the simulation for you, this is done here. And the worker strolling speed or walking speed is kept as 80 meters per minute, which is the standard that is given by International Labour Organization, ILO. That is one of the things that is taken into consideration here. Also the variability, that is the total availability is taken as 95% for each of the processes here, that I can show you here. Let me show you the failures. You can see 95% is the availability here. 95% availability. So those things we have put here, and we have tried to obtain a factory that is producing the goods, and the total throughput is shown in the report as we have seen. So for the workers, the starting scenario was 1 worker per activity, as I said, total 6 workers, and it was found similar throughput that is possible for 4 workers as well. Similar, it was not exactly same for 5 and 6 workers. The throughput was completely similar, but for 4 workers it was a little lesser than 5, but that was acceptable. For the line 1, it was something like this. If I say worker 1, 2, 3, 4, 5 and 6, and this is a throughput. It is, let me say, 170 here, and it is coming down like this. So this is workers or number of workers. Okay, 1, 2, 3, 4, 5, 6. So this plot came something like this, till 4 workers, 1, 2, 3, 4. It was okay. From 4 to 5, throughput was like this, and from 5 to 6, it was exactly same. So selecting 5 workers was the first option, okay, but there was a little variation, only this little variation, this small increase or small improvement in the number of units that those are produced. So there is always a trade-off, whether the worker, the pay that we are going to worker is that high, or the number of units those who are producing, the profit that we get from them is that higher. So depending upon these, we can see whether to select 4 or 5 workers, but yes, out of 5 and 6, 5 workers were selected. So this was for the selection of workers, and for the throughput I have told you how the variability was shown, and also I would like to show how the charts looked like, the utilization. Let me say show chart. So this is a chart that is developed, only the green color here shows the working time, rest is the blocked time or setting time. Setting time we cannot ignore. Working time is okay when the machine is actually working, and block time, yes, that can be worked on. Waiting time can be worked on. Now blocking here means this is blocked for this much of time. We say this is percentage of time from 65 to 97 something. For 22% of the time, the single process 1, that is electrical laser sintering, is blocked. That means the successive machine, that is post processing, is taking longer time, and this machine is waiting for its own the pieces that it has manufactured to ship to the next machine. So what we can do, we can put a buffer in between to store the pieces, or we can add one more post processing machine, that is CNC machine. It all depends what do we need to, what is the total investment that we need to make. We need to just maximize the throughput, number 1. Based upon throughput and the cost incurred, we get the total profit. The overall aim is to maximize the profit. This I have discussed in costing as well. This is break-even point. Whatever criteria gives us the earlier break-even point, and we get the better profit, that is taken into account. So this is plant simulation 10 that we have discussed, and how factory design can be simulated using any of the softwares. Those are capable to do this. One of the softwares we have discussed. And with this, my part in the course is over. Professor Ramkumar will take one more lecture in which he'll take the case studies on rapid manufacturing, the 3 specific case studies on different fields. 3 fields those are taken are medical sciences, number 2 is automobile and aerospace, and then we'll conclude the course. Thank you for being in the course. You're welcome to ask any questions. Prepare well for the exam. Just follow the notes those we have given, and also try to read the books those are given in the reference in the different presentations and the course homepage. Thank you so much.